Modern vehicles are not engineered to fail after exactly 5 years, but automotive engineers and industry analysts have documented that specific components in current production vehicles are deliberately designed to minimum cost and minimum service life targets that align with warranty expiration and average vehicle ownership periods, creating a pattern where expensive repairs cluster predictably between 75,000 and 150,000 miles on vehicles that previous generations routinely drove past 250,000. The distinction matters. Cars aren't programmed to self-destruct. But the engineering decisions made during design and the materials selected during manufacturing reflect financial targets as much as reliability targets, and the result for consumers is a statistically predictable wave of repairs that arrives just after the original warranty ends. Automotive industry consultant data and independent reliability surveys, including Consumer Reports' long-term reliability tracking, show measurable differences in component longevity between vehicles built in the 1990s and early 2000s versus vehicles built in the last 10 years, with modern vehicles showing higher rates of expensive electronic and powertrain failures in the 75 to 125,000 mile range. The mechanisms aren't conspiracy, they're economic. Warranty coverage periods define the minimum acceptable component lifespan for manufacturers managing warranty cost reserves. Turbochargers and direct injection systems that improve fuel economy ratings also create new failure modes that didn't exist in simpler engines, and proprietary software controls that require dealer diagnostic equipment intentionally limit independent repair options. Keep watching, because I'm going to explain exactly which systems fail predictably and why, show you the engineering decisions that created these failure points, and tell you how to protect yourself from this pattern. Hey, if you like this kind of straight-to-the-point content with no BS, help me out here. Subscribe to the channel right now. It takes 2 seconds and guarantees you won't miss any tips that could save you some serious cash. Let me start by explaining the economic framework that shapes automotive engineering decisions, because understanding the business reality makes the engineering choices logical rather than sinister. When an automaker designs a vehicle, engineers work within cost targets that determine every component specification. A component that lasts 300,000 miles costs more to manufacture than one that lasts 150,000 miles, using more material, tighter tolerances, or better alloys. The manufacturer's financial incentive is to use components that outlast the warranty period, reliably enough to avoid warranty claims, but not necessarily components that outlast the vehicle's potential service life by a factor of 3. The warranty period in the United States is typically 3 years or 36,000 miles bumper to bumper, and 5 years or 60,000 miles powertrain. These periods represent the manufacturer's guaranteed commitment. The engineering target for most components is to perform reliably through the warranty period with acceptable statistical failure rates, not to maximize longevity beyond that threshold. This isn't unique to automobiles. Consumer electronics, appliances, and most manufactured goods follow the same economic logic. The difference with vehicles is that the cost consequences of component failure are dramatically higher. When a smartphone battery degrades after 2 years, replacing the phone costs a few $100s. When a turbocharged engine's timing chain tensioner fails after 90,000 miles, the repair costs $3,000 to $8,000. The second economic factor is the aftermarket parts business. Many automotive manufacturers derive significant revenue from replacement parts, dealer service, and extended warranty products. A vehicle that requires no dealer service after the original warranty expires generates no ongoing revenue. A vehicle requiring periodic expensive repairs at authorized dealers generates profitable service revenue. This creates a financial incentive structure that isn't aligned with maximum consumer vehicle longevity, even if individual engineers working within these systems genuinely prioritize quality. The third factor is fuel economy regulations. Federal CAFE standards require manufacturers to meet fleet-wide fuel economy targets or pay significant penalties. To meet these targets, manufacturers introduced smaller turbocharged engines replacing larger naturally aspirated ones, direct injection systems replacing port injection, dual-clutch automated manual transmissions replacing conventional automatics, and cylinder deactivation systems that shut off cylinders during light load driving. Every one of these technologies improves fuel economy ratings while introducing new failure modes that didn't exist in the simpler, mechanically robust systems they replaced. Now, let me explain the specific components that fail predictably in modern vehicles, and the engineering reasons each fails when it does. Turbocharged engines have become standard equipment on vehicles that previously used larger naturally aspirated engines. A turbocharged 4-cylinder replacing a naturally aspirated 6-cylinder delivers similar or better fuel economy with comparable power, but the turbocharger adds a component operating at extreme temperatures that the base engine never experienced. Turbocharger bearings operate in oil that reaches 300 to 400 degrees Fahrenheit at the turbocenter housing, far exceeding the oil temperature in the rest of the engine. When drivers shut off a hot turbocharged engine immediately, residual heat soaks into the bearing oil, cooking it and leaving carbon deposits that accelerate bearing wear. Turbocharger replacement costs typically $1,500 to $3,000, and failures cluster between 80,000 and 150,000 miles on vehicles where owners didn't allow cool-down periods or used conventional oil. This failure mode didn't exist on naturally aspirated vehicles. Direct injection systems introduced to improve combustion efficiency create a different problem: intake valve carbon deposits. In traditional port injection engines, fuel sprays directly onto the back of the intake valves, washing them clean with every injection event. In direct injection, fuel injects directly into the combustion chamber, bypassing the intake valves entirely. The valves accumulate oil vapor deposits from the crankcase ventilation system with nothing to clean them. After 60 to 80,000 miles, significant carbon builds up on the back of the intake valves, reducing airflow, causing rough idle, hesitation, and reduced performance. Professional carbon cleaning using walnut shell blasting costs $500 to $1,500 and is required on many direct injection engines at intervals the owner's manual doesn't mention. Dual clutch transmissions, marketed as offering the efficiency of a manual with the convenience of an automatic, use two clutch packs operated by computer-controlled actuators. When functioning properly, they shift faster than human drivers and improve fuel economy. When the clutch wear, hydraulic actuators fail, or the transmission control software has issues, repairs cost $3,000 to $7,000. Ford's PowerShift dual clutch resulted in a $35 million class action settlement. Volkswagen's DSG transmission has documented reliability issues. The failure rate on quality conventional automatic transmissions from the same era is dramatically lower. The timing chain system in many modern engines represents a third area of predictable failure. Older engines used external timing belts that were easily replaced as scheduled maintenance, typically every 60 to 90,000 miles. Modern engines largely replaced timing belts with timing chains, expected to last the engine's life. However, several manufacturers implemented timing chain systems with small, lightweight chains, plastic tensioners, and variable valve timing actuators that introduce wear and failure points the older belt-driven systems didn't have. BMW's N47 diesel timing chain, Chevrolet Ecotec timing chain, and Ford EcoBoost timing chain issues are all documented examples where chains and tensioners failed between 80,000 and 150,000 miles, costing $4,000 to $10,000 to repair. Now, let me explain how to protect yourself from predictable modern vehicle failure patterns through informed purchasing and maintenance decisions. Research reliability data before purchasing any vehicle. Consumer reports, annual reliability surveys, J.D. Power Vehicle dependability studies, and owner forums provide real-world failure rate data by make, model, and year. Avoid first model year vehicles with new technology because first production years have higher rates of problems as manufacturing processes mature. Wait for the second or third model year of any new platform or powertrain for others to identify and publicize problems. For turbocharged engines, extended oil change intervals are the enemy. Turbocharged engines require oil changes no longer than 5,000 to 7,000 miles, regardless of what the manufacturer specifies, because the high heat environment degrades oil faster than naturally aspirated engines. And turbocharger bearing health depends directly on clean oil. Use full synthetic oil meeting the manufacturer's viscosity specification. After any hard driving, idle the engine for 2 to 3 minutes before shutting it off, allowing turbo-bearing temperatures to drop before oil flow stops. This dramatically extends turbocharger life. For direct injection engines, use a quality fuel injector cleaner like Chevron Techron or Redline SI1 every 10,000 miles to minimize intake valve deposits. Some manufacturers now use both port and direct injection simultaneously to maintain valve cleaning, so check whether your engine uses combined injection, which eliminates the carbon deposit problem. For dual clutch transmissions, check whether your specific model has had documented reliability issues before purchasing. If you own a vehicle with known dual clutch problems like early Ford Focus or Fiesta with PowerShift, keep detailed maintenance records and understand your warranty and extended warranty rights. For timing chain systems with documented issues, research technical service bulletins for your specific vehicle. Manufacturers often issue TSBs acknowledging problems and specifying updated parts or procedures. Some extend warranty coverage on components with documented systematic failures. Consider extended warranty coverage on vehicles with known problem components if you plan to keep them beyond the original warranty period. The extended warranty math favors buyers of vehicles with documented failure patterns in the 75 to 150,000 mile range. Select vehicles with proven mechanically simple drivability designs if reliability is your primary concern. Vehicles like Toyota Camry and Corolla, Honda Accord and Civic, and Mazda vehicles consistently demonstrate better long-term reliability, partly because they've been slower to adopt complex new technologies and have refined their existing platforms over many years. The most reliable modern vehicles use naturally aspirated engines, conventional automatic transmissions, and proven engine management systems rather than cutting-edge fuel economy technologies, except that some additional fuel cost from a simpler powertrain may be significantly less than the repair costs associated with a technologically complex but failure-prone alternative. So here's the bottom line. Modern vehicles aren't programmed to fail after 5 years, but economic and regulatory pressures produce engineering decisions that result in predictable expensive failures clustering between 75,000 and 150,000 miles. Turbocharged engines, direct injection systems, and dual-clutch transmissions, and cost-minimized timing chain systems all introduce failure modes that simpler systems didn't have. Protect yourself through pre-purchase reliability research, aggressive maintenance, especially on turbocharged engines, early adoption avoidance of new technology platforms, and realistic expectations about the cost of owning complex modern vehicles beyond their warranty periods.